Hi everyone, my name is Jan Drgonia, and together with my colleagues Aaron Tour and Draguna Vorabie from Pacific Northwest National Laboratory, we are going to show you how you can combine deep learning and physics for cutting the cost of advanced building controls. The fact is that buildings use almost 40% of the global energy and then generate 20% of the greenhouse gas emission. The problem is that current building controls are very inefficient. They are implemented in a set of static rules and independent PID loops. On the other hand, advanced controls such as model predictive control has been identified as a potential solution for energy efficient building operation with energy potential savings up to 30%. In fact, in our field's case study in a real office building in Belgium, we have demonstrated that advanced physics-based model predictive control can get even higher with energy savings more than 50% while still improving thermal comfort. Now imagine the global impact of leveraging the full potential of this technology. However, there is a catch. The design and implementation of these physics-based controls is very tedious and costly and requires months of development time of the physics-based models. And this hampers the widespread adoption of this technology in practice. Here we take one step back and look at this problem from a more abstract perspective and simplified physics-based modeling. We can represent the building as a structured graph model where each component has its dynamical interaction with each other. For example, we have weather and occupancy, building envelope, HVAC, and actuators. And you have corresponding physics-based equations. Now we leverage this prior knowledge and we design this physics structured neural model where each of the components of this neural model now has a physical interpretation in a building model structure. And the main advantage of this structured model is that now we can apply the prior knowledge, constraints, and structural priors into each component's blocks to assure the physical coherence of this model. We implement this novel deep learning-based approach on a large-scale data set of the office building with 20 zones. And we can demonstrate that using only 10 days of the training data, we can generalize over consecutive 20 days on the open loop dynamics without great loss of accuracy. In fact, we demonstrate more than 50% reduction in error compared to the state of the art. Now, when we have a physically coherent and accurate physical model of the building, next successive step is to design advanced predictive control. Here, the idea is to reformulate the classical model predictive control constraints as a constraint deep learning model, which consists of the learned structured recurrent dynamical network of the building behavior and the control policy, which together form closed loop dynamical systems, which we can now train end to end. We demonstrate this novel physics-informed differentiable predictive control on tutorial system with linear dynamics affected by parametric and additive uncertainties. And we show that we can control the state trajectories to remain within prescribed bounds and track the desired reference where the effect of uncertainty is shown in error bars. We assume the constraint control action and also effect of the weather forecast and occupancy. What is important to emphasize is that we are able to train these generalizable constraint control policies given only small amount of data. We are using 1 week of training data set, and we are able to generalize over consecutive 2 weeks, which are outside of the probability distribution of the original data set and are affected by disturbances. We can further improve the control performance by applying online learning in adaptive control fashion. In conclusions, we have presented generic data-driven modeling of the building thermodynamics, which is physically coherent, interpretable, and sample efficient. We are using this model to design end-to-end learning of the constraint control policies just from time series data without manual and tedious modeling. In fact, we can, in such ways, we can cut the development time from months to days. Therefore, we believe we have market-ready solution, and our future work is focused on the large-scale deployment and demonstration of this technology in real-world buildings. For more details, please visit our papers, our implementations in PyTorch, and here I would like to thank you very much for your attention.